All right, so that handout is the Section 1 notes. That's going to be the last printout that I give you. So if you want, Section 1, 2, 3, 4, so forth, they're online. So you need to print those off before the next couple of days. We don't get too far through those today. So by Monday, I would think you maybe need the second section. Okay, so have those printed off by Monday if that's the route you're going to go. Just real quick, the way that this class is kind of set up is that early on we are going to be doing some review of solving certain types of equations. This first chapter is analyzing initially linear equations, then we get into quadratic equations, we look at graphing inequalities and that kind of stuff, solving root equations. That stuff's going to happen early on. It is a review. Now I know that we are at different levels in that review, so but we all passed 8th grade algebra, algebra 1. So today's stuff, I'm not going to spend time, hey, you got to add 5 to both sides. You got to divide by 4 to both sides. Like, I'm not going to do that with you. Instead, we're going to talk about like what is happening in the background of why maybe my solution is what it is and how I can use that information to help me solve maybe equations that are completely foreign to me, I've never seen before, even without the instruction on how to do it. Okay, so I'll give you that kind of background a little bit today. So first thing is solving linear equations, okay? If I'm going to solve a linear equation, I got to know what they look like, okay? And that's something that we go through the entire year. Each type of equation has its own kind of predefined procedure, right? To use the correct procedure, I've got to be able to correctly identify, okay? So does anybody know what the generic form for a linear equation is? Anthony? Okay, ax plus b equals c. Okay? In my opinion, that's the best answer you can have. Okay? Some textbooks will go ax plus b equals 0. And that really says the same thing. It's just that we've moved c over to the left-hand side, and b and c are constants, and we just combine them. Does that make sense? Okay. So either one is fine. Last class, somebody said y equals mx plus b. That's fine. It is a linear equation, but it's a linear equation in 2 variables. Okay. Which is something we'll graph, but we're not going to solve that. Does that make sense? Okay. If I'm going to solve a linear equation in 2 variables, I need a second linear equation in the same 2 variables. So that's what we're going to look at now. The one thing that we got to pay attention to here is when we start providing things like this. Okay. So this is the general form. Okay. So basically that gives me the infinite number of possibilities. Like this one here would be, if this is general, this one would be specific. Does that make sense? Okay, because I got specific values for A, B, and C. So what I need to do here is I need to write semicolon where A, B, and C, I'm going to write that weird looking E, okay? It's like it's not that E. That E means something else, okay? So it's a curved E, kind of like a C with that line, okay? And then I'm going to put that there, okay? Does anybody know? This is the math notation. This is stuff that we're going to periodically target as we go through this class. One of the things that I found when I entered college mathematics, excuse me, was my lack of experience with notation, okay? In high school, if I didn't know what the notation was, I just kind of skipped over it and assumed that, well, I'm going to take the view that doesn't really matter, okay? Well, if you do that enough, that kind of snowballs and creates big issues for you, okay? So in a lot of classes, they just introduce it. Like when I was in high school, they would just introduce it and never talk about it, okay? Even in college, they just introduce things and never talk about what it means, okay? So you've got to do that kind of investigation on your own. What does this symbol mean? Does anybody know what that means? I can't hear you. Okay, so I'm not going to disagree with that. The best, she said, they're equal to being real numbers. What if I did this? What if I said, what do you think that means? They're in a third period class. So that E means that they belong to third period class. Yes? This year? It's an R, but it's a special R. So we'll get to it. Okay. So that E, and I think that's what you were talking about, right? Is that they're equal to the correct phrasing when we look at that E is that we read it as A, B, C are elements, and there we see where the E comes from, of, okay, so that E stands in, it's a shorthand for the phrase, are elements of, okay, which, if you want to even put that in the further layman's terms, you can say belong to or come from. Does that kind of make sense? Okay. Now the capital R with that extra stand on it, okay, those are your what? Real numbers, okay? So that is all real numbers, okay? Which essentially is every single number you can imagine, okay, except for square roots or even roots of negatives, okay? Because those are then your imaginary, okay? And they help create what we call our complex number system, okay? Which we'll get into in this course, but right now you're probably most familiar with just the real number system, okay? Which basically just says all your numbers. But if I were to say like integers, you guys know what those are? They are real numbers, but real numbers are not integers, okay? So your integers are your whole numbers, 0, 1, 2, 3, 4, and their opposites, so -1, -2, -3, okay? And what I mean by, so, like, 1/2 is a real number, is it an integer? No, okay? So there, I'm saying a real number is not necessarily an integer, but an integer, like 5, is that a real number? Absolutely. Every integer is a real number, but every real number is not an integer, okay? So our number sets, and that'll be like, we have an entire section dedicated to that, are going to be important to us in this course for the mere fact that when we come across certain theorems, certain laws that we have to abide by, they're going to be identified by saying this there if yada 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 comma then yada 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 for A, B, and C being elements of integers or elements of whole numbers, or K has to be a natural number, something like that. Does that kind of make sense? So our theorems are going to use those key words: real number, natural number, integer, rational number, that kind of thing. And if we don't know what those categories are, which we'll work on if you don't know them right now, you're not going to be able to utilize that theorem correctly every single time. Okay, so we'll hit that pretty hard eventually. Okay. When we look at the linear equation, the key identifying component to it being linear is that exponent right there. An exponent, the greatest exponent in the equation is 1, and it's in the numerator, okay, then you have a linear equation. And linear just means that when you graph it, you get a line, okay? So let's go down the bottom here, where it says, can you tell a difference? Okay, is that first one there, is that linear? Yep. Okay, what about this one here? Is it linear? 2x plus 3x equals 1. Yeah. Most people are going to rewrite that as 5x equals 1, right? So usually the best time to make a conclusion is once you've combined like terms. You don't need to, but that is, I think, the best time. So this is linear. What about this one here? Why not? Okay, good. So that exponent there tells me right away this is non-linear. Okay. You said it gives me a parabola, which is the graph, right? So the one thing about like lines, linear gives me a line, right? So like line corresponds graphically to this equation's parabola, right? Like the parabola is the word that we use for the graph, but what is the equation? What type of equation is that called when it has a power of 2 being the greatest? Quadratic, okay? So that's a quadratic. Quadratic is a form of nonlinear, okay? Right now we're just classifying as linear or nonlinear. In the last class we kind of made the argument. It's like saying if I look at people and I say, is this person a freshman or not? Well, if they're a freshman, they go in that group of being a freshman. But if they're not, does that narrow my focus on what they are? No. They could be a sophomore, a junior, a senior citizen. They could be an infant. Does that kind of make sense? Okay. So just because I've got linear and then nonlinear, that nonlinear group, guys, is very, very vast. Okay. And part of this class, a lot of this class is actually going to be looking at how we deal with those nonlinear equations and how we solve them and how we interpret them and all that kind of stuff. Okay. Now, what's the exponent right now for this x the way this is written? Do you guys agree that exponent's 1? If it's not written, it's an understood 1. So is this linear or nonlinear? We're saying linear because exponent 1, right? Okay. However, where is the variable? Denominator. So do you guys remember last year that if I've got rational exponents, or not, I don't want to say that rational terms, and I want to move variables, I can move that thing up there with that 3, right? You guys remember how to do that? Remember that? Now, usually, you're actually presented with that form last year, and then asked to rewrite it, and we know that we don't like negative exponents, right? And if you forget your rules of negative exponents and why, we can go 3 over x and rewrite that as 3 times x to the negative 1. We'll get into that later this year. Okay, it's just subtraction essentially. Does that yellow thing have a greatest exponent of 1? No. So that's nonlinear, right? Okay. That is actually what we call a rational function. What's the root word for rational? Ratio. Ratio means comparison of two things through division, right? Which is a fraction, right? So if you ever have, now this is when it's fully simplified, because I can give you a rational function up there that once you simplify it turns into something that looks linear, okay, or is linear. When you have a simplified version of something and the denominator has a variable in it, it's rational. It's nonlinear. Okay? Is that cool? All right. Now, one more thing to talk about. We'll just talk about this conditional. We got types of linear equations, okay? And basically, types of linear equations is analogous or corresponds to the number of solutions that you can have for a linear equation, Okay? 99% of the time, you've dealt with linear equations and you've gotten one answer, right? Okay? The other 1%, we'll talk about probably tomorrow, you've seen them, but they were things that maybe you in a homework assignment in Algebra 1 of like 30 questions, maybe you saw it like 3 or 4 times. So it's something that wasn't really embedded into your mind. But when I have a linear equation, I can have one answer, 0 answers, or infinite answers. Okay, and we'll talk about those here. The first type is what we call a conditional linear equation. Okay, and it basically talks about my solution. What is the condition? And when I say condition in mathematics, it means it's a requirement I have to make, right? Before something is true, it's a requirement that I have to meet. So, for instance, we get out of here at noon, right? Okay. You can only leave this classroom if it is 12 o'clock. That's the only time you can leave, right? So we have to meet the condition of 12 o'clock before you can exit, right? So when I say condition, it means it's something that you have to abide by before that second half comes, right? We call that a conclusion, which would be the second half, okay? You guys remember talking about if-then statements in geometry? Okay. The if part was the hypothesis, the then part was the conclusion, okay? Those were collectively called conditional statements, okay? So what is the value of x? What is the value for that to be true? X has got to be, it's got to be 3, right? So if x is 3, then 2x minus 1 equals 5. That's a conditional statement. Does that make sense? So that's why that's called conditional, okay? No other value of x ever makes that true, okay? So how many solutions is that? It's just one, right? So a conditional statement or a conditional equation has one true answer, okay? Now, something I want to talk about, there's a couple different varieties of ways of looking at this, okay? Can I rewrite this as 2x? Can I go 2x equals 6? Would that be okay? Can I write it as, now this is how I would solve it, but can I write it as x equals 3? Okay? So I'm just going to number these. I'll start off with like 1, call that 2, call that 3. What about if I go, could I have done this? Could I go 2x minus 6 equals 0? Okay, so that would be fourth option. Okay. Now, if I was going to solve that, logically, it probably makes sense to move the 6 over, right? But can I do this? Can I go negative 6 equals negative 2x, something like that? I'll stop. There's some others, but I'll stop there. And the reason I want to show you this is to provide you with logic of what's going on in the background. Okay? We know the answer should be 3, right? So I'm just going to go to GeoGebra here. And if I ever come across an equation that I don't know how to solve, or maybe I do know how to solve it, but I'm lazy, and I want to expedite the process a little bit. When solving an equation, the logic behind the scenes is that the left-hand side is a line, okay, in regards to linear equations. If it's nonlinear, maybe it's a curve, intersecting a line, or two curves intersect, something like that. But I'm going to let the left-hand side be y equals 2x minus 1. I'm going to let the right-hand side be y equals 5. I'm going to graph those and see what I get. So y equals 2x minus 1, and y equals 5. And I get those two lines, right? Now they intersect, and that's the thing that I'm interested in. What's the x value of where they intersect? 3. What am I always solving for when I solve an equation that has a variable of x in it? X. So the intersection is 3, 5. The x value there is 3. That's the solution to the equation. Does that make sense? Okay. Now, as I start to manipulate that equation, when I'm going through that analytical approach, okay, and trying to like write it as 2x equals 6, let's look at that graph real quick. I'll do it in the blue here. If I go y equals 2x and y equals 6, okay, now, those two lines, they look a little bit like this one because they still have the same slope of 2x, but it's been shifted up, right? So that red line right there is different than this one, right? This red line here is different than that one. This one's going through 5, this one's going through 6. But where do they intersect? Still intersect at 3, right? Now the y value is different, but they still intersect at x being 3. And what you do to one side, you do to the other side. Okay? We've always talked about keeping the equation balanced, right? Graphically, what it does is it guarantees that the solutions to the original problem are still existing in the manipulated version. That make sense? Okay. Bring that tomorrow. We'll pick up from there. We'll start talking about those other possibilities for linear equations.